Okay, so the last little bit we're going to talk about in topic 5.2 is about the concept of resistivity. Now, resistivity is not to be confused with resistance. Okay, the two words are related to each other, but they're not the same thing. Okay, so we've already seen in the past the definition of electric resistance. And electric resistance is defined as the ratio of the voltage across an object to the current through that object. Okay, and so now we're going to look at how you can actually calculate the resistance of an object based solely on its physical parameters. Okay, and so when I say an object here, the most common way that you see resistivity problems involve calculating the resistance of wire. Now, up until now, we've basically been going under the assumption that the wire in a circuit has no resistance, okay, which is not necessarily true. Right, and so we have an equation that allows us to calculate the resistance of a wire, not just a wire, but any solid object, based off of some physical properties. Okay, and so here is the equation to do that calculation. This equation is given to you in the data booklet. Okay, R, of course, we know is resistance. Okay, we give the Greek letter rho as a symbol for what is called resistivity. Resistivity is a value that depends on what the material making up the object is. Okay, and so for example, copper would have one set resistivity, silver might have another resistivity, gold would have another resistivity, iron, and so on. Okay, and so resistivity is basically a number that quantifies how much resistance a certain type of material has. Then you have a capital L, which represents the length of the object. And again, when I say object, the easiest example to think of in your mind is like a wire. Okay, so this would be like how long is a wire? And then divide by A, where A is what's known as the cross-sectional area. Okay, so cross-sectional area. And we've actually seen that term cross-sectional area before in the context of drift velocity. Okay, and so if you imagine looking at a wire, okay, so imagine you take a wire, you cut it, and you look at it from the side, what you see is a circle. Okay, so when we talk about the cross-section of an object, we're basically talking about it, cut through and then looked at from the side. Now, if you're talking about a wire, of course, that cross-section is a circle. I have seen IB questions with resistivity involving like a rectangular prism type of deal made out of metal. In fact, I've had people do IAs based off of that type of um, object. Okay, but most of the time, at least more than half of the time, the object you're talking about with resistivity problems is a wire, and so the cross section would be that of a circle, which you should know, of course, is pi r squared. Make sure when you are calculating cross-sectional area that you make sure to convert the units correctly. Now, resistivity has units of ohm meters. You can show that pretty easily just by rearranging this equation to get resistivity by itself. Um, but it has units of meters, and again, that depends only on the material um, that the object is made of. All right, so for example, if you were like some type of engineer who routinely had to use resistivity values for stuff, then you would basically just look up a table of resistivity. Okay, so here we see some common materials um, and their respective resistivities. You can also look up this kind of thing online. I think if I get to the internet, I can find a chart with resistivity on it. Okay, and so this is just taken from Wikipedia. Obviously, if you're an engineer, you probably wouldn't be using Wikipedia for a reference. You would probably have your own like reference guide with different resistivity values. Although I do want to point out, this is probably too hard for you to read, or the text might be too small. But objects like glass or rubber, those have a very, very high resistivity, which makes sense because they are insulators. They're not conductive. Okay, and so of course you would expect like metals, which are conductors, to have very low resistivity values, and then insulators would have very high resistivity values. All right, and then this just kind of summarizes what we've talked about so far. Now, a few things I want to point out is that basically what you can infer from this equation is that the resistance of an object, or the resistance of a wire, just to talk about a specific object, increases if the resistivity value is higher. It also increases if the length of the object is bigger. Okay, you can see that here from the equation. If L is bigger, if you multiply by a bigger number, you get a bigger value for R. Okay, and that makes sense if you think about it, because if you have a wire that's very long, the longer it is, the more difficult it is for charge to flow through that wire. Conversely, it is inversely proportional to the cross-sectional area of the object. As you can see in the equation, we are dividing by area, and so if you think of a wire, think in terms of thickness. The thicker the wire is, imagine the wire being like a pipe for those electrons to run through. Okay, the thicker it is, the bigger the cross-sectional area, the easier it is for those electrons to flow. Okay, because there's like literally more space. All right, it should be common sense. If you have a bigger pipe, more water can get through. Um, and so the wider, or the larger the cross-sectional area, the lower the resistance. Okay, so let's do some basic examples. So example 1 says, use the table to the right to determine the resistance of a 4-meter long wire with a 2 mm diameter that is made of the following materials. And I'm only going to do one calculation because I don't really want to do more. Okay, so we have a table of resistivity given to us right here. And let's do it for copper. Copper is very commonly used, partially because it has a low resistivity. It doesn't have the lowest resistivity though. In fact, if you look at this chart, you'll see actually silver has a lower resistivity. The reason we don't use silver in wires is because it's not as commonly found. It's much more expensive because of its rarity. But just based off of the electrical properties, it might actually be better to make wires out of, because it's got lower resistivity. All right, so if I want to find the resistance of a wire, the equation is rho times L over A. Rho is the resistivity, so for copper, that would be 1.68 times 10 to the negative 8. It's kind of hard to read on this table, but that's what it says. L is the length of the wire. Do make sure that the units are correct. Notice that if the unit for resistivity is ohm meter, that means everything needs to be in meters or meters squared. So when I go to find A, that's the cross-sectional area. For a wire, that's going to be a circle. And so I want to do pi r squared, but I need to remember to convert this to meters. And notice this is actually the diameter. So if the diameter is 2 millimeters, that means r equals 1 millimeter. Okay, so into my calculator, I'm going to do pi times 1 times 10 to the negative 3 squared. Okay, and so for A, I get approximately 3.1 times 10 to the negative 6 meters squared, and then it's just a matter of plugging that in. Okay, so I'm going to do 1.68 times 10 to the negative 8 times 4 divided by 3.1 times 10 to the negative 6, and I get 0.022 ohms. Okay, now if that seems like a small value, it is a small value. Okay, that's way smaller than 1 ohm. Usually we're dealing with resistors that have like 10 or 20 or 100 or 1,000 ohms. And so that's why in most situations we really ignore the resistance of the wire. Technically there is a very small voltage drop inside the wire itself just because of its resistance. Because remember, voltage drop is given by V equals IR, but notice that the resistance of a relatively long wire, 4 meters is pretty long for a wire. Even that long of a wire has a relatively low resistance. Okay, and so even though it's not zero, usually when you're doing calculations, you can ignore the resistance of the wire. Okay, so pause there if you need to look at that some more. Okay, a couple more quick examples. That's just another basic calculation question. I don't know if we need to do another one of those. I do want to look at a proportional reasoning question. We've seen this type of question many times before. Okay, so here it is in terms of resistivity. Okay, so a proportional reasoning question is one where we're asked, like, basically what happens to something if something else changes. Okay, so here it says the resistance of a wire of length L, cross-sectional diameter D, and resistivity rho is R. Determine the new resistance of a wire with a length of 3L and a diameter of 2D. So in other words, we are making the length 3 times longer, and we're making the diameter 2 times bigger, and the original resistances are what is the new value of the resistance if we make these changes. Okay, now first of all, recognize they give us the diameter D, but that's not really in the equation. Okay, so first, it should be an L. So first, let's write the equation in terms of um, diameter. Okay, so if it's a wire, it's going to be pi r squared, or we could say D over 2 squared. Okay, and so that would be rho times L. There's a pi and a d squared on the bottom, but we're also dividing by 2 and then squaring it. Okay, so that's going to become 1/4. And because we're dividing by a fourth, the 4 actually like flips over and ends up on the top because that's what happens when you multiply and divide by fractions. Okay, so this is our original expression for R. Now we want to find a new R when we make the changes they ask us to make. So we keep the resistivity the same. We triple the length. Okay, so L becomes 3L. And then we also double the diameter. Okay, so on the bottom we have pi times D squared. All right, and so that is going to become 3 rho L over pi D squared. And this type of question you often see as like a multiple choice question. Okay, so we want to find the new resistance as a multiple of the original resistance. Okay, and the easiest way we can do that is just to divide these two. Okay, so what number should go in this blank? That would just be r prime over r. And so if I do 3 rho L over pi d squared, if I divide by my other expression, remember when you divide fractions, wow, when you divide a fraction, you flip the second one and you multiply. I should have taught you that in like elementary school or middle school or something. And the pi cancels, the d squared cancels, the L and rho cancel, and we just get 3 over 4. Okay, so in other words, making these two changes is overall going to decrease the resistance by 3/4. Okay, it's going to be 75% of the original value. So that's just your standard run-of-the-mill proportional reasoning question. We've seen that type of question many times before. Here we're just seeing it in the context of a resistivity problem. Okay, so pause there if you need to look at some more. Okay, so the last thing we're going to talk about in this video is we're going to start talking about 5.3, which is called electric cells. And we're just going to run through the very basics of how a cell works before we end this video. Okay, so in 5.3 we talk about cells, internal resistance, secondary cells, terminal voltage, or what they call terminal potential difference, but we call terminal voltage, and what's called EMF, electromotive force. At the end of 5.3, you must be able to investigate practical electric cells, describe the discharge characteristics of a simple cell, identify the direction of current flow required to recharge a cell, um, determine internal resistance experimentally, and then solve problems involving EMF, internal resistance, and other electric quantities. So that's the one we're going to spend the most time on down there. Okay, students should recognize that the terminal voltage of a typical cell loses its initial value quickly, has a stable and constant value for most of its lifetime, followed by a rapid decrease to zero as the cell discharges completely. Okay, and so anyone who's ever like bought batteries before knows that's how most batteries work. Like it works and then it dies really quickly. Now, if you buy a rechargeable battery, then you can actually recharge it by putting it in a special type of charger that basically runs a current through the opposite way. But not all batteries are rechargeable. Okay, so we're just going to run through this kind of quickly. Not that it's not important, it's just you typically see questions involving uh, calculations in this unit. Okay, so let's just really quickly go through the basics of how a cell works. Okay, so a cell, or battery is like a combination of cells. You basically have a weak acid and you have two electrodes made of different metals. Okay, and we're not going to get into like the chemistry side of how this type of thing works because this is not chemistry. But basically, the different metals dissolve in the acid at different rates, and so you end up with ions going um, into the liquid solution. Okay. Um, the weak acid, in this case, we call the electrolyte. Um, we call the least negative metal the positive terminal, and the most negative metal the negative terminal. Okay, that's why you have to be careful with batteries, by the way, because they do have acid in them. Okay, and so basically what a cell does is it expends chemical energy um, and turns it into electrical energy. We talked about this at the beginning, but um, if you think of the purpose of the voltage source to kind of lift positive charge up to a higher voltage, and then um, it goes around the circuit and the process repeats itself. I had some people ask me like, why would the positive charge inside the cell go from negative to positive? Because that shouldn't happen naturally, and that's true. And so what causes it to happen is like a certain type of chemical reaction that we're not going to talk about. Okay, but cells do convert that chemical energy into electrical energy. All right, there's two types of cells, and this is not something that's commonly assessed, but it is technically part of the IB curriculum. So just so you have these definitions, a primary cell is a cell that cannot be recharged, and a secondary cell is a cell that can be recharged by applying a voltage, basically reversing the chemical reaction that is undergoing here. And that's all I'm going to say about primary and secondary cells. I almost never see questions about them on the IB exam, but in case you ever do, there you go. Now, this we've seen before. The definition of electric potential difference, delta V, is defined as the amount of work done in moving a positive charge Q from a lower potential energy to a higher point of electric potential energy. And we've kind of seen something like this before. I think maybe we wrote it in terms of like the work needed to move the charge. Um, Either way, this is basically how um, electric potential difference is defined. Okay, so it is the electric um, potential energy per unit charge. All right, so if you take a charge and you move it um, from a higher potential to a lower potential, basically what's happening is it's going from a lower potential energy to a higher potential energy. And the change in potential, the potential difference is just the change in electric potential energy divided by the charge. All right, so the unit for potential difference, aka voltage, is volt, which we know, which you can also write as joules per coulomb. And all of this we talked about like a long time ago. I'm just kind of recapping. Let's see, we talked about the cell using chemical energy, blah, blah, blah. Just to do like a really base calculation with this type of thing, let's say we had 200 microcoulomb of charge brought from an electric potential of 2 volts to an electric potential of 14 volts through use of a car battery. What is the change in potential energy of the charge. And this is just a really simple, basic type of calculation involving like potential energy and charge. Okay, we know from like a couple of units ago that you can figure out the change in energy just by taking the charge and multiplying by the potential difference. Okay, so here in this case, 200 microcoulomb, that's 200 times 10 to the negative 6 times the potential difference. If it's going from 2 volts to 14 volts, that is 14 minus 2. And you can see what the answer to that is down here. And if it seems like I'm going through this quickly, it's just because even though you do sometimes see these calculations, this is not the main part of what I want to focus on in 5.3. It is assessed like occasionally, but not super commonly. And plus, this is all stuff you should know from past units anyway. Okay, I do want to introduce a new term though before we end this video. Okay, and so this is a term that is called electromotive force. This fancy looking E, okay, it kind of looks like a 3, but it's backwards. Okay, this E is a symbol for electromotive force, or as we call it, EMF. Now, it has a very bad name because it is not a force at all. Force is measured in newtons. Somebody named it like a long time ago before we knew what was actually happening, and the name kind of stuck. And so, electromotive force is not actually a force because force is measured in newtons. But basically, the idea is they gave it the name because this is what like pushes the charge around the circuit. Okay, so the electromotive force, the EMF of a cell, is defined as the amount of chemical energy converted to electrical energy per unit charge. Here I will say, by the way, definitions are important. I'm always reminding you of that. Okay, now what we have here is we have a digital multimeter acting as a voltmeter. Notice, by the way, it is connected in parallel to a battery, and it gives us a reading. It gives us 1.6 volts. Okay, so what we would say is that this cell has an EMF of 1.6 volts. This is what we call the unloaded reading of a battery or a cell. By unloaded, I mean it's just the cell by itself. It's not hooked up to a circuit or anything like that. Okay, just the cell out in the wild. We're just sticking a voltmeter on it, seeing what it says, 1.6 volts. Now, something kind of interesting happens though. If you take this cell and you hook it up to a resistor, this is what a resistor looks like right here. Okay, if you hook it up to a resistor, you get a slightly different reading. Notice now that the digital multimeter is reading 1.5 volts. Okay, so let me just draw the circuit diagram for what you're seeing here. Okay, so originally what we had like a slide ago was we had a cell and it was basically in parallel with a voltmeter and it was reading 1.6 volts. What we're now seeing here, over here to the right, we see it's actually connected through a wire to a resistor. And so basically what we see now is we have the same cell, we have a resistor, and then we still have like a voltmeter hooked up parallel to it. I'm just putting the voltmeter down here just for space. Okay, now this voltmeter is reading 1.5 volts. So this is kind of a curious thing. Okay, this is what we call the cell being loaded because now the cell is actually hooked up to an external circuit. And notice that the loaded voltage across the cell is slightly less than the unloaded voltage. Okay, so the EMF of the cell is 1.6 volts. While the cell is hooked up to a resistor, we get a reading of 1.5 volts. Okay, so something is going on inside that cell because you wouldn't think like just because it's hooked up to a circuit, you wouldn't think that the voltage of the cell itself would change. Now, obviously, there would be like a voltage drop across the resistor. We would expect that. Okay, but we're not losing 0.1 volts in the resistor. We're losing it inside the cell itself. Okay, and so I'm going to stop this video here and kind of leave you with that mystery to think about where is that 0.1 volts going, and we will continue talking about that in the next video. Okay, as always, please let me know if you have any questions, and I'll see you guys in the next video.